Okay, hello everyone. We are at section 1.2. As you can see, systematic lists. Our objective today is just to be able to use kind of a very structured list to approach a problem methodically, step by step, and to use it to either count or to organize or to solve a problem. So I'm going to start with a very simple question, and that is for you to think of a mathematical formula that does not have an equal sign in it. I think that most of you are familiar with the Pythagorean theorem, a squared plus b squared equals c squared. Most mathematical formulas use an equal sign. Well, we're actually going to use one today in this section that does not have an equal sign in it. So you can pause if you want and think about it, but the answer to this little puzzler is what's called the triangle inequality. And that is just that if you have any triangle with sides A and B and C, and we can just say that C is the longest side, we'll assume that C is the longest side, that it must be true that A plus B always has to be greater than C. And if you think about it, that if you swing an arc that would go through the vertex of A and C and come down to some point on C, and we did that to B, well, they've got to be together longer than C, because if it was too short, when these swung down, they would not be able to touch, and they would just lie flat on C, and you wouldn't get a triangle at all. So the triangle inequality is one of the few times in mathematics that we get a formula that does not have an equal sign. It has an inequality. Okay, so what we're going to do is I'm going to do a couple of simple examples from the book, because in years past I've seen that relatively easy problems are confusing because you're not used to this book, you're gearing up to doing homework in it first couple of days, and it's tougher. So I'll do a few examples. First one is what is the fewest number, okay, I'm back, there was a little technical difficulty there. We're going to look at problem number 9 in the book just as a good example to get started. And that is just if we had a triangle with a perimeter equal to 17 whole units, what are all of the possible combinations of whole number sides that will give us a perimeter of 17? So we could start with a chart. And if you think, what's the longest possible side that will give you 17? So this is like side A, side B, and here is side C. And together they all have to equal 17 units. Well, clearly if you have 1 and 15 and 1, it's not going to make it because the 1s will not bridge that gap. So I need, if I even try 4 and 4, that makes 8. But 8 plus 9 will make 17, so that's not good enough. So for the isosceles triangle, at least, I could start with 5 and 5 and 7. And that will give me a triangle, because 5 plus 5, our two shorter sides, add up to be more than 7. But clearly 4 plus 4 does not add up to be more than 9. And then I can, to keep it isosceles, I can try 6 and 6, and then take away 2 and make this 5, and that's going to work. That any two sides add up to be greater than the next one. Let's see if it goes 7 and 7 and 3, that will make a long skinny one. And then 8 and 8 and 1. So these are all of our combinations that will give us isosceles triangles. Okay, well then I'll leave it to you to find the rest. That will be scalene triangles. But that's sort of a systematic list that will help you find all of the possible triangles that have a perimeter of 17. Okay, then I want you to take and look at page 12 in your textbook and read probably page 13 and read through those problems, but then particularly in the top of page 14, problem number 16. I want you to read that, see if you can figure it out, pause, and come back. Okay? I'll wait. Okay, so by now I hope you've looked at problem number 16 on the top of page 14, and this is an example of both what's good and a little bit frustrating about our textbook. They've got really kind of a cute real-world problem about grooming animals, and they've got nice little pictures of these fuzzy little beasts, but then the book, for some reason, decides to hide the information all over the place, and I think maybe it's because in real life you're going to have to go and find information from a variety of sources. You'll notice some of the information is below the picture, some of the information is actually in the body of the problem there, where it says that part-time workers work 3.5 hours a day. And then most of the important information are in these charts. There are many problems in the book where you have to find information in those 3 places, in the problem, in the pictures, and then in a chart. And just get used to it and expect to see it in your homework. Anyway, I've made my own little systematic list just to help you understand the problem. Long-haired dogs take 85 minutes to groom. Short-haired dogs take only 20 minutes. Cats take 25. And then just the plain flea treatment takes 15 minutes. And then the longest you could possibly spend on any one animal is the long-haired dog with the flea treatment. There are 4 of those. 85 minutes on long-haired dogs only, and so on. The various combinations getting you down to a variety of different animals that I kept tallies that were just getting the flea treatments. Okay, so if you look at the example in the book, they talk you through a method of, after you've organized this data into a systematic list, how you string the list out and you start taking the highest numbers possible to piece together how many workers you're going to need. So for instance, you could have one person do 100 minutes and then 100 minutes, and then nothing else will keep you at 210. So you can take and put this down to 2, and you've got 1 worker in your tally. And then the next worker, you can say, well, you've got another 200 minute, and again, they're just below their limit, and then there's another worker, and that's all done. And then you start with an 85 and an 85, and that gives you 170. Well, we've got up to 210, so then you can go to the 40, and that gets you right at 210. So you take away 2 of these, you've got only 1 left. Take away 1 of those, you've got 1 left, and you're down 3 workers. So that's one way you can do it. You can continue my method, or maybe you'll come up with a better one on your own. Okay? The homework will be appearing on the next screen, and you're good to go. See you tomorrow.